Welcome to the video podcast series at Ontario High School. We're dealing with the essentials of acids and bases, and I believe this will be entitled Acid-Base Fundamentals Part 2. But if you're watching this, that won't much matter. You're here. So in this particular podcast, we're going to deal with strong and weak acids and bases, how we identify them, and especially how we write the net ionic equations for reactions that involve strong and weak acids and bases. So, welcome. Thanks for being here, and stay tuned. In the previous podcast, part 1, I gave you a list of strong acids, and I said that there are 7 strong acids. There are thousands upon thousands of weak acids. The best way to know whether an acid is strong or not is to memorize the ones that are strong, that list of 7, and then every other acid that you see will be considered weak. Now, the definition of a strong acid is that in aqueous solution, it will ionize 100% to hydrogen ion and the iodide ion. And we talked in our earlier podcasts as well that the hydrogen ion, H+, really doesn't exist independently in aqueous solution. It actually combines with water molecules to form H3O+. Fortunately, chemists, for simplicity's sake, will accept it written as either H+ or H3O+, as will I. So, and as will the AP chemistry test. So for that, we are fortunate and grateful. But these are the 7 strong acids that in water will ionize 100% to H+ or H3O+, and then whatever the anion is. So please memorize these, and when they are involved in a chemical reaction, make sure that in aqueous solution you always write them as their ions and not in their molecular form. The molecular form for hydroiodic acid, for instance, is HI. Its ionized form would be H+ or H3O+, plus I-. So, and that's true for the rest of these. Of particular note is sulfuric acid down near the bottom, and we'll talk about that in more detail later. Now let's look more closely at H2SO4. It's the only polyprotic or diprotic acid. When we say di or polyprotic, most of the strong acids, as we saw before, are what are called monoprotic acids, meaning they have just one proton or H+ ion to donate. But H2SO4 has 2. Remember that poly is a Greek prefix meaning many. So it has more than one, which fits into the polyprotic category. And because there are 2, we would call it diprotic. Now, when H2SO4 ionizes, it does not ionize to 2H+ and SO4 2-, but only the first hydrogen ion ionizes 100%. So when we write the ionization of H2SO4 sulfuric acid, it's going to go H2SO4 becomes H+ aqueous and HSO4- aqueous. Now, this is true for solutions that are stronger than 0.0001 moles per liter. Solutions weaker in concentration than that have a slightly different dynamic, but we're not going to deal with that here. For our purposes, we will write H2SO4 as though it were stronger than 0.0001 moles per liter, and in that case, it is experimentally observed to ionize just one hydrogen. The HSO4- is a weak acid that contributes additional protons, and we'll deal with that more when we get into acid-base equilibrium, which is coming up in a future podcast. But just make this note for now, and this will carry us through. The other thing that you'll want to see with HSO4-, we talked about the meaning of amphoteric when species can act as either an acid or a base. And here we have an example. HSO4- can donate a proton and become SO4 2- and H+. So it has an acid behavior, but it can also accept a proton. It's the conjugate base of sulfuric acid, so it can accept a proton and form H2SO4. So it also has a behavior as a base depending on the circumstances. So this is what amphoteric is, and it would do you well to remember that. Here is a table of strong bases, and a strong base we're just going to define as one that completely ionizes in water to give one or more hydroxide ions, or OH minus, per base molecule. Group 1 metal hydroxides are strong bases. Here you see sodium hydroxide, potassium hydroxide, lithium hydroxide, rubidium hydroxide, and cesium hydroxide. And then there are two group 2 metal hydroxides that are considered strong, albeit they are very only slightly soluble. And so for that which is dissolved, however, group 2 metal hydroxides for calcium hydroxide, barium hydroxide, and strontium hydroxide, those will ionize to their metallic ion, Ca2+, Ba2+, Sr2+, and then 2 hydroxide ions per molecule of the metal hydroxide, or formula unit would be a better way to put that, of the metal hydroxide. Well, when we talked about weak acids and strong acids, we said that all the acids not listed with the strong acids are considered weak. And basically this just means that they ionize less than 100% in aqueous solution, and it's usually much, 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 much less than 100%. A very common weak acid that you're familiar with is acetic or ethanoic acid, and weak solutions of acetic acid are vinegar, and you're used to vinegar in terms of both as a cleaning agent and part of certain salad dressings. So that's where you may see that. Now, acetic acid or ethanoic acid can be written several ways. The first way you'll see more commonly in inorganic chemistry textbooks, the HC2H3O2. The CH3COOH is the way that organic chemists would write this. And that COOH group is very significant. It's called a carboxylic acid group or carboxyl group. And anytime you see COOH on a molecule, it is a weak acid, or at least has a weak acid component to it. If you have been through biology or anatomy and physiology, you have seen this when you study amino acids. All amino acids have carboxyl groups as part of their component. Now, one of the things that you're going to notice is when we write a reaction with acetic or ethanoic acid and water, it does not ionize 100%, and so we put a double arrow there indicating that this is an equilibrium reaction. And you can see that acetic acid will donate a proton to water in small amounts and form the acetate ion there as well. So that's how you would write the reaction of acetic acid or ethanoic acid in water. Okay. For weak bases, any base that we didn't list as being a strong base, and the strong bases, by the way, are all hydroxide bases. So most weak bases, however, are not hydroxide bases, and we'll get into that more as we go. But the ones that are not hydroxide ion containing bases react with water to hydrolyze water molecules, and that results in the production of hydroxide ion in small amounts. And an example of this is ammonia, NH3. When NH3 reacts with water, you see the double arrow again here because this is an equilibrium reaction. It goes both ways in a dynamic equilibrium. But the ammonia molecule, NH3, will hydrolyze water, and what we mean by hydrolyze is it will split a hydrogen off in small amounts from water molecules and form the ammonium ion, NH4+, and the hydroxide ion, and that would explain its basic behavior. We want to be able to write the net ionic equations for neutralization reactions. And one of the things that you'll see on the slide is a basic format for neutralization reactions. Acid and a base form salt and water. And one of the things that we have to qualify here is that This general formula of acid plus base yields salt plus water is when you have a base that contains the hydroxide ion. And that's very important to note. There are some bases, we just talked about one, ammonia, that does not contain the hydroxide ion. And so when you neutralize ammonia, it's going to be a little bit different. But when we get there, you'll be able to pick that up. So the keys are this, that strong acids and bases must be written in their ionized forms, meaning, for instance, for HCl, you would write it H plus Cl minus. And sodium hydroxide, which is a strong base, you would separate the sodium ion and the hydroxide ion when you write the equation. Weak acids and bases must be written in their non-ionized forms. So as their formula unit or molecular formula, that is what would be included. Only the species that change, either in formula or phase, from the reactant side to the product side are included in the net ionic equation. And those are the two keys. So we're going to do a sample problem together and you'll see how this works. Let's look at a sample problem here. It asks us to write the net ionic equations that describe the following neutralization reactions. And what I'd like you to do is to pause the podcast when it's appropriate and write these equations down, and then write what you think the net ionic equations for these reactions are, and then resume the podcast and see how you did. Now, one thing, if you're totally clueless at this point as to how to do this, you can go ahead, pause the podcast, write these equations down, resume the podcast, and just work through the solution with me of the first two, and then pause the podcast again and see if you can get the last three on your own. So that's my recommendation for you. The reactions are right here. So pause the podcast. When you come back, we'll start working through these one by one. Now we've come to the end of part A, and it has ended with a sample problem in which you're going to write 5 net ionic equations. Part B will have the solutions, and what I would recommend that you do is try your best on these. And again, just look at Part B if you're having trouble with the first couple. Check out the HCl and the CH3COOH reactions, and then pause it after you watch those work through and see if you can finish the other 3, as I reinforced before. Now, I want to leave you with a quote from Richard Milhous Nixon, famous American president. "A man is not finished when he is defeated. He is finished when he quits." My recommendation to you is that you do not quit at the end of this podcast, but that you go on to Part B and see how these are worked through. So I wish you well.